Hello, Chem 120 students. This is the first lecture for Chapter 7, which is on atomic structure and periodicity. I will warn you that my assumption in this lecture is that you have watched the 3 videos that I highlighted in the Chapter 7 curriculum. If you haven't watched those, they are posted on Blackboard under Chapter 7 lecture materials. They just do a really good job of introducing some of the larger concepts in this chapter, which is going to help us not have a very long series of lectures to watch. Okay, so the last chapter was on thermochemistry, and we were really interested in the way that energy is transferred in the form of heat in chemical reactions. Now we're going to be interested in energy in the form of electromagnetic radiation. So electromagnetic radiation is otherwise known as light. We usually are talking about light in the range of, fat marker, that's right, 400 nanometers to 700. The reason why we often talk about light within that range is because that is the visible spectra for human beings. And of course, we're really interested in all of that. So we want to talk a little bit about some of the characteristics of electromagnetic radiation, which I'm just going to abbreviate as EMR. So there's 2 big characteristics that we want to make sure we're familiar with. The first one is that electromagnetic radiation has wave-like behavior. And the second is that it travels at the speed of light in a vacuum. It's going to be a really important concept as we move through this material. Okay, so here our spectrum is going from gamma rays to radio waves, with that thin slice of visible light kind of being pulled out for us so we can see the spectra. Should look familiar, like the colors of a rainbow, right? All visible light. Okay, so if you look, we have gamma rays, which have a wavelength. So wavelength is increasing across our axis here, or horizontally. So gamma rays, we have a wavelength of 10 to the negative 12th, which we know is going to be really, really small, right? That would be on the picometer scale. And then here we have radio waves at 10 to the 4th. And this is in terms of meters, that's our unit. So you can think of that as being quite long. So we know that radio waves are pretty safe. We hope they're safe anyway, they're all around us. They have these really long waves. Gamma rays are really, really short waves, and these are going to be higher energy. And we'll talk a little bit about that in a second. Okay, so there's kind of 2 ways that we talk about, or 2 characteristics that we use to define a wave, and that is going to be wavelength and frequency. So wavelength we just saw on that last slide, and that is going to be the distance between a peak and a trough. So let me just draw a wave here. Okay, so one wavelength would be peak to peak. And the symbol that we use for wavelength is lambda. So it's that little funny backwards K, if you will. So peak to peak or trough to trough would be one wavelength. So here that's being shown in each of these 3 examples of waves. So wavelength is peak to peak, trough to trough. Frequency is the number of waves that pass in a given period of time. Okay, so let's just look at that for a second. So let's say we're talking again about radio waves. And let's say that the particular radio wave that we're looking at, it takes one wave 5 seconds to go peak to trough. Its frequency would be 0.21 over S. Right? So per second, 0.2 wavelengths would make it through like a frame. In contrast, if we had gamma rays, we would have something more like, let's say, this is a kind of arbitrary number, 400 waves in 5 seconds. And then you would have a frequency of 880. Yeah. So this illustrates a really important concept, which is that wavelength and frequency are inversely related. So if you have a really long wavelength, it means that you're going to have a very low frequency, like we just saw with our 0.2 frequency for those radio waves. In contrast, if you have a very short wavelength, you're going to have a really high frequency. All right, and that's what this is showing here. So wavelength, our unit is going to be meter, right? Our symbol is lambda. Here our symbol is nu, and our unit is 1 over S, 1 over seconds, or per second. You can think of it that way. That can also be written algebraically as seconds to the -1. And we have a unit that we call hertz that also describes frequency, which is abbreviated Hz. So remember that waves travel at the speed of light in a vacuum. So the speed of light is 2.9979 times 10 to the 8th meter per second in this class, and in most classes, you're just going to call that 3. Cool. So there's some concepts in defining terms for waves, which is the way that we're first going to be exploring light, right? We know from watching those videos that light is both has both particle and wave characteristics. So we start with waves, talking about electromagnetic radiation in terms mostly of light. Okay, so we have this simple formula and we're just going to apply it to a word problem. So we have an FM radio station broadcast at 99.5 megahertz. Calculate the wavelength of the corresponding radio waves. Okay, so remember, speed of light is the speed at which light travels in wave travels in a vacuum. We have that being equal to its wavelength times its frequency. So here we're given the frequency of 99.5 hertz. And we know that C is the letter that we ascribe to assign to the speed of light, and that is 3 times 10 to the 8th meters per second. Oh, sorry, this is megahertz. Okay, so one thing to pay attention to is that we're using the metric system here, and this is mega. And our constant is meters per second. So that's not megaseconds, it's just seconds. So just like we saw with our ideal gas law constant R, we need to honor the units of our constant. So the first thing that you want to do when you're solving for wavelength here is convert your megahertz to hertz. So if you look on your periodic table that I give you at the beginning of the semester, you'll see that in the metric conversions table, there's mega, and it is 10 to the 6th, in this case, seconds. So to use our conversion factor would be, yep, let's do it that way, I guess, 99.5 megahertz. Right, and 1 megahertz would be equal to 10 to the 6th hertz. right? 1 over seconds. So that would be 9.95 times 10 to the 7th hertz. Okay, so that is our unit for frequency in a form that agrees with our constant in meters per second. So I want to just go ahead and rearrange our variables to isolate for wavelength. So that would be wavelength is equal to C divided by nu. So our wavelength would be equal to 3 times 10 to the 8th meters per second over 9.95 times 10 to the 7th hertz. Remember, hertz also equals 1 over seconds, or seconds to the negative 1. So the seconds are going to cancel out when you do your algebra. And you plug that into your calculator and you should get 3.01 meters. Oh my god, it's just doing something cute. Sorry. Okay, simple math, just applying this concept that if a wave is traveling at the speed of light in a vacuum, then if you take the product of its frequency and its wavelength, it would have to equal the speed of light, right? Its rate. Okay, so we just have one more just to warm us up so we feel really good about math. Here we have the laser in a CD player, right? Who has those anymore? Uses light at a wavelength of 7.8 times 10 to the second nanometers. We have to calculate the frequency, and we have our constant, 3 times 10 to the 8th meters per second. Okay, so just like before, we need to honor the units of our constant. So we need to convert nanometers to meters. So remember that relationship is 10 to the negative 9th. So this would be 7.8 times 10 to the second nanometers. 1 nanometer is 10 to the negative 9th meters, which means that that would be 7.8 times 10 to the negative 7th meters. So we take our 3 times 10 to the 8th meters per second, rate of the speed of light, divided by 7.8 times 10 to the negative 7th meters. Meters is going to cancel out. We're left with 1 over seconds, otherwise known as hertz, otherwise known as our frequency. Plug that into your handy dandy calculator and you get 3.84 times 10 to the 14th. Cool. Okay, so the math for these problems really isn't too complicated. Just a 3-variable problem for you to work through. Okay, so here we've been kind of exploring light as a particle, or sorry, light as a wave, but now we're going to pivot and kind of look at some of the mathematical relationships that let us know that light was not just simply a wave, but it could also be thought of as a particle. So a lot of that work was done by Max Planck, and he was studying dark bodies, and discovered that energy could only be gained or lost in these whole unit multiples of HV. So what that means is that if you were measuring the energy gained or lost by a object, so you can think of that as like a light bulb, you would expect to see a continuous spectrum, right? Where you would have something like, you know, this. Right? Maybe it's not a linear relationship, but whatever. You have all of these points on a line that are continuous. So you could have that energy be any value at all in the universe. What Max Planck discovered instead is that it was actually a discrete relationships. So you can think of discrete as being points on a field. So this isn't any single value is possible like you would have for a continuous spectrum, but instead you had these very discrete amounts of energy that could be gained or lost. That energy we now call a quanta, which is the root for quantum mechanics, if you're familiar with that at all. Pretty cool. You can definitely go down a YouTube rabbit hole exploring those concepts. But Planck's work came to the creation of H, which is Planck's constant, and that is 6.626 times 10 to the negative 34th joule seconds. Okay. So this is going to be energy gained or lost by whatever it is you're studying. In his case, he was looking at incandescent bodies. So this is our constant. This is our frequency. N here is going to be an integer. Now, usually when we're looking at Planck's constant, we're interested in the energy of one quanta. And so usually N is going to equal 1. Now, it doesn't always have to equal 1. In fact, we'll see an example later in the lecture where it doesn't equal 1. But it is worth saying that if the question is like, what is the energy of a photon of one thing, then it would just be delta E equals HV. If instead, for some reason, you wanted to know what the energy associated with 5 quanta, it would be N would equal 5. That's not really a terribly practical question. We're usually not interested in that. We'll see that we would be thinking about quanta in much larger values. Okay, so H is this like proportionality constant that is defining this relationship between energy and frequency. Okay, so let's see this in action because I think it really kind of helps to explain this concept. So we have the blue color of fireworks is apparently achieved by heating copper chloride to a really hot temperature. It causes the compound to emit blue light, having a wavelength of 450 nanometers. Cool. What is the increment of energy, the quanta, that is emitted at 4.50 times 10 to the second nanometers by copper chloride? Okay, so this value, hopefully, you recognize as just being 450 nanometers converted into scientific notation, somewhat annoyingly, but that's okay. So our equation that we just learned was that our change in energy is equal to NHV. Again, we're interested in the increment of energy, so that would be by one quanta, so every quanta of copper chloride at that wavelength. So this is another example where our N would equal 1, so we can essentially just neglect it. So that change in energy is going to be equal to Planck's constant times our frequency. Okay, so another thing for us to pay attention to is that we're giving wavelength, which is most often what's going to happen. So remember that our speed of light equals our frequency times our wavelength, which means that our frequency would be equal to c over our wavelength, which means that while, yes, this is our given equation, we can also use these two relationships to derive another equation that lets us relate the energy associated with that wavelength of one quanta. Okay, so that's just like a neat little mathematical trick that will help you when you work through problems. Okay, so that wavelength is 4.50 times 10 to the second nanometers. We are going to be using the speed of light. C, we need our meters to cancel out, so I need to convert nanometers to meters. Remember, 1 nanometer is equal to 10 to the negative 9th meters, so this would be 4.5 times 10 to the negative 7th meters. Okay, everything else that we have is a constant. So our delta E is going to be equal to Planck's constant, which is 6.626 times 10 to the negative 34th joule seconds times the speed of light. Divided by our wavelength of 4.5 times 10 to the negative 7th meters. You plug that in and your delta E is going to be equal to 4.41 times 10 to the negative 19 joules. Pretty cool. So what does that mean? That means that every quanta, so every photon, we'll come to call that. Sorry, my dog just got in from outside and he always likes to say hi. Is going to have 4.41 times 10 to the negative 19 joules. In this case, that would be what is emitted, right? So released. So every single photon would have, or quanta would have that energy. Very cool. It's cool that we can calculate that. Okay, so Einstein kind of took Planck's concept of quanta being these like packets of energy that were transferred or gained or lost by something, and he kind of took it and ran with it, developed the photoelectric effect, which is what he won the Nobel Prize for when I think he was 26, which is kind of crazy. And the photoelectric effect is pretty cool. This figure here is kind of showing some of the, a little bit of the concept behind it. So here we have red light, which is at a lower frequency, longer wavelength. If you shine it at a metal foil or a piece of metal, nothing's going to happen, right? If you use green light, higher frequency, and you shine it at that same metal, then you are going to be able to eject electrons, right? So those photons, the quanta of energy, these packets of energy, are displacing those electrons. So Einstein used the photoelectric effect to prove the particulate nature of light, so the concept of light as a particle. And you can see this is really just Planck's constant, only now instead of saying it as a quanta, this like change in energy gained or lost, instead we're looking at it as the energy of a photon. Very cool. Good old Einstein. He also has a quote that if you didn't make a significant scientific contribution by 30, you never were. Or maybe it's 40. I'm 35. I think my boat sailed. Sorry, Einstein. Okay, so let's do a problem that kind of helps to illustrate this a little bit. So what we're going to find is that this is very similar to our last problem with Planck's constant and that energy of copper chloride. So this is the same equation, only now we're thinking of it in terms of a photon as this particulate nature of light. So a photon of ultraviolet light possesses enough energy to mutate a strand of human DNA. True story. Wear your sunscreen. What is the energy of a single UV photon in a mole of UV photons having a wavelength of 25 nanometers? Very cool. Okay, so 25 nanometers, again, we're using wavelength, so we are going to be using this form of our equation. We need to convert our 25 nanometers to meters. So 1 nanometer is 10 to the negative 9th meter. So it'd be 2.5 times 10 to the negative 8th meter. The energy of that photon is going to be equal to our Planck's constant, 6.626 times 10 to the negative 34th joule times seconds, times our speed of light, 3 times 10 to the 8th, divided by our wavelength, 2.5 times 10 to the negative 8th meters. Okay, so let's go ahead and plug that in to our calculators. And I get 7.95 times 10 to the negative 18th. All right, so that is the energy of one photon of in the ultraviolet spectrum with a wavelength of 25 nanometers. Very cool. So that's half of our question. The next half is what is the energy of a mole of those photons? He's just learning to bark. It's very cute. Come on, where's your ball? I'm sorry. Exactly. He's very cute. Okay, so energy photon, 7.85 times 10 to the negative 18 joules. So remember that this is the energy associated with one photon. So that is per photon, right? We want to know how much it would be per mole. Well, we know that 1 mole is 6.02 times 10 to the 23rd of anything. The little thuds you're hearing is my dog pushing a ball into my lap and then letting it fall off. It's very exciting. Photons and 1 mole. We're probably going to have to take a little small break after this. So plug that into your calculator and you're going to get 4.8 times 10 to the 6th joules per mole. Okay, so that is just one application of the Planck's constant in relationship to energy of a photon. Pretty indicative of the kind of work that you'll be expected to do in analyzing a energy associated with light at a wavelength. Right, so we've talked about light as a wave, looking at frequency and the wavelength. Now we also have this concept of that light being a particle capable of displacing electrons from a metal surface, and this idea of it being a discrete amount of something. So it's not continuous, like a wave is continuous, right? It's discrete like a particle. So you already know where we're going a little bit with this, but just from watching those videos. But so we have this dual nature of light. And you're never going to use E equals mc squared, but I do think that it's really valuable to recognize that our understanding of light does entail that that light has mass, which would be something that we don't think of for like electrons or things that have a wave-like nature. So this is a really hard concept. It's something that has been the subject of so much debate for, hundreds of years. It's pretty cool. So one example was Young's double slit experiment. There's some awesome YouTube videos about this. Some of them get like really weird and start talking about the matrix, but it is this cool part of our existence, which is that, light is both a particle and a wave. And we're going to see that we will start to think of that as electrons being both particles and waves. So if you take a piece of cardstock, let's say, and you cut 2 slits in it and you've shown a light through it, on this piece of paper that would be directly behind that paper with 2 slits, you would have what is called a diffraction pattern. So what's significant about this is if you had light as particles, you would just expect those particles to basically form 2 piles, right? Like you can think of if you took, actually, let me just go ahead and do this. If you took this image and you rotated it, right? And this were just a countertop, and that was that cardstock with 2 slits in it, and you were pouring salt, right? Here, we'll make it Himalayan pink salt. And you were to pour it through those holes, you would end up getting a pile with most of the salt directly opposite those holes on either side. And that would be that. And it would be cool and it would be understandable and you'd be like, yeah, that's a particle. So we've just been talking about light as a particle and having these like discrete values to it. And now we see that it's not just that simple. It's also a wave. So when you shine light through here, you get diffraction patterns. These are showing those waves where you have points where the waves interfere with each other. And in those spots, oh, sorry, I didn't mean to use that. In those spots, you have these dark lines, right, where basically the light cancels each other out. Then you have these points where the light is going to be like contributing or amplifying each other when 2 waves meet. And those are the spots where you get the really bright lights. So this is called the diffraction pattern. And it's something that only waves are capable of. Okay, so the videos that you watch do talk about this concept as well. This is also just a book, if I can give a little plug for it. It does a great job. It's a popular science book that looks at this double slit experiment. It does an awesome job of kind of explaining all of the great minds in science that were involved in figuring out the dual nature of light and these like huge debates between the greatest minds of all time that revolved around quantum mechanics. So I'll end this lecture on this slide just because this is like the coolest room ever. So it's the 1911 Solway Conference, and it was a gathering of the brightest minds in physics, chemistry, mathematics, all in one room together talking about amongst other things, the nature of light. So I just have some of the gentlemen in the room highlighted for you. This is Ernst Planck. This is NERSS. The NERSS potential is something that you'll learn if you do any kind of human physiology. We have de Broglie, we have Rutherford, who we have talked about, who we've talked about in this class in that gold foil experiment. We have Einstein, very young. Marie Curie, I just highlighted. We've never really talked about her in this class, but that's a lady in the room. So let's point her out. Yeah, awesome. Also, I like this image because this guy isn't actually there. That's like one of the oldest forms of Photoshop I've ever seen. He was in the bathroom. Yep, you can kind of tell. You can kind of tell he wasn't actually there. Or maybe it's this guy. No, it was that guy. Right, the scale's all off. Anyway, That's just a fun fact for you. Wish I could have been in this room. If the subject of this chapter is really interesting to you and that dual nature of light, read this book. It's really interesting. It's really simply written. I thought it was a super fun read. I'm also a super nerd though, but maybe you are too. Okay, so that's a really good foundation for chapter 7. There'll be one, maybe 2 more lectures, but I'm going to try to keep them short like this one. So don't forget to watch those 3 videos, and I will see you soon, virtually.